next presenter will be Mr. Hugh Carrick. Hugh is a space systems engineer at ASTRO, the Australian space technology research organization based in Melbourne. ASTRO aims to help in advancing the new space industry within Australia by developing innovative open source technologies for future space missions. He is the creator of Linear Electromagnetic Accelerator for Cubesat science missions, and he leads ASTRO's liquid propulsion development program and originally designed the avionics package for the HeartStar mission. Stage is all yours, Hugh.
Awesome. All right. Thank you very much. So I did fly up from Melbourne. It's a few degrees cooler there. I do have a cold at the moment, so I'll stand close to the microphone so I can't project. But yeah, so I'm a propulsion and avionics engineer for our Cubesat stuff at ASTRO in Melbourne, as well as the Linear Electromagnetic Accelerator. So ASTRO was formed last year after the IAC. We met a bunch of really passionate, young, enthusiastic engineers who work on their own space projects. They don't work for companies or organizations who are doing this. They're just like-minded and they love space, so that's why they do it. We're a lot more of a collective than a company. We just sort of share ideas, we bounce theories off each other and help out where we can. We're not profit-driven. We don't have any funding. We all do it ourselves. But we are focused around making our technologies open source when they're mature. We've got people from a wide variety of fields, both space and non-space, IT, engineering, bioscience, even some ethanol production. They're looking at liquid fuels with some interesting additives based on ethanol and methanol. So about me, I don't have an aerospace engineering degree. I'm a software dev with some electrical engineering background. I do non-space in the 9 to 5. I'm a full stack software dev, so this is my daily life. I do have background with electrical engineering and some mechanical as well, though, but mostly it's just set over block. So linear electromagnetic accelerators. Let's get to the good stuff. So linear electromagnetic accelerators. What are they? How do they work? And what are their applications? Well, a linear electromagnetic accelerator, break it down, is basically anything that takes electricity, dumps it through coils to create a magnetic field, and then use that to attract a payload or repulse it and give it some momentum direction. So typically, charge up some electrolytic capacitors, dump it through some coils, this creates a magnetic field, and then you've got some motion. So LEAs today, they do exist in the world. In the military, you've got coil guns and rail guns, great for blowing people and things up. For transport, you've got maglev, great for moving people around. And for space, you've got mass drivers on paper. Obviously, there's some challenges with mass drivers. They're really a holy grail of space propulsion. They're up there with space elevators, unintended. But they are typically kilometers long. They require national level funding. And as long as you're launching them from Earth, then you've still got to deal with an atmosphere and things like that. So until we're building on the moon, a bit of an issue. So a picture you have got your mass driver. You condense it down to the size of a CubeSat. What can you do with it? If you look at the traditional rocket equation, you accelerate the payload in one direction, satellite moves in the other. So is it a satellite propulsion subsystem? It does provide some delta V on the order of about 25 meters a second if you're using it from about 400 kilometers and launching, say, 25 payloads. But it's inefficient. You don't want to use it as a main propulsion engine. What they are good for is if you look at the other end of the rocket equation, it's not fuel that you're sending out there. It's not combustion byproducts. This can be an actual self-contained scientific payload. So sensor suites, transmitter, batteries, your whole shebang. You're sending it on a different orbit or an atmospheric injection trajectory. So self-contained payloads. We're lucky enough to live in a world today where single chip electronics are getting massive, and by massive I mean tiny. So this is a commercial off-the-shelf radio transmitter from Texas Instruments. But that board isn't the transmitter. That tiny, under a single square centimeter is. And these are some of the chips that we're focusing on with our LEA payload development. So that's a CC2250 and a CC1050. Those are the two that we're currently experimenting on. They're about yay big, they're cheap as pennies, and they work. So what are the applications for atmospherically injected payloads? I should mention there are basically two. you can consider with a linear electromagnetic accelerator. Either you're accelerating things into a different orbit, or you're accelerating them towards the atmosphere, pushing them in the retrograde, killing off some delta V. So, climate change modeling and weather monitoring, obviously a big one. We already use satellites extensively for developing our weather models, for predicting significant events, but satellites can only really look at the weather that's going on below. They can't really touch it, they can't feel it, they can't experience what's going on. So if we bond together a bunch of atmospheric sensors together with a transmitter and put it onto atmospheric injection trajectory, you get to sample that atmosphere, every single layer, as it's going into perhaps the eye of a hurricane or an ash cloud, a plume from a volcano, and get some really concrete data. I mean, they're currently throwing away some UAVs flying these things on suicide missions, but yeah, it's just a different approach. So also ablative materials testing. Currently NASA Ames, they have their plasma wind tunnel where they bombard these new materials with thousands of degrees of plasma. And it's good for developing models such as like glass buildup, but it doesn't have the same structural loads that real atmospheric re-entry will encounter. And so what we propose is building up these sensor packages, slapping the ablative heat shield that you want to test on the front, and actually firing into the atmosphere, because that's a lot better to test. So, applications for dynamic orbit payloads. This is where you're not sending it towards the atmosphere, you're either just changing the trajectory, the plane, the altitude, etc. So if you consider Sherpa from spaceflight, they built this tug, which is designed as a primary payload on a launch vehicle, and it carries a whole bunch of CubeSats as its own primary payload. It's able to deploy these CubeSats into all different orbits, trajectories, inclinations, you name it. And it does this with fairly high on-orbit life and a multiple engine restart capability, but it uses traditional chemical propellants to do so. If you consider instead a satellite about the size of the Hubble, a little bit bigger, but it's got a linear electromagnetic accelerator as its payload. Instead of a CubeSat with a LEO firing payloads that are about the size of your pinky finger, what we're considering is sending actual CubeSats. So you're using a Hubble-sized satellite to launch CubeSat-sized satellites onto all different sorts of trajectories. Probably not into the atmosphere, you don't want to throw away the CubeSats, but maybe perhaps onto things like translunar injection. The delta V is certainly there, but these things scale bigger, better. The bigger you get them, you can send things onto Mars, et cetera, et cetera, et cetera. So ASTRO is developing a couple of CubeSats, they're our own. We've got two currently in development in parallel. So we've got HeartStar and Shooting Star. HeartStar is a 1U CubeSat. They both share a common avionics, and HeartStar is designed to test these avionics in flight. So it's all bespoke, it's all designed ourselves, it's a learning experience for us, self-funded, so it's good fun. It's there to confirm some of our design decisions, validate our ground segment that we're also building, and we're targeting a launch late 2021, because that's when I'll be able to save up for it. It is amazing that we live in a day and age where a launch cost really isn't out of pocket if you've got a full-time job. So, Shooting Star is our 3U that we hope to launch afterwards, and it is designed to actually test a linear electromagnetic accelerator in orbit. So, uses a common flight avionics heritage, so we'll wait until all the tests are done, etc. And we're going to look at carrying some research payloads on this. So if you've got any ideas of something you want to shoot into the atmosphere, maybe we can make some fireballs and correlate some things. And we'll launch obviously in late 2022 plus. So I don't know how much time I've got, but I'll just blaze through some of this because we do have a patent pending on some of the LEO stuff, so I can't actually talk about the specifics of how we're going to operate, but this is some of our heritage design. So this was like 2 years ago plus, some awful folding solar panels that wouldn't have worked. Quickly realised that. This is just tests for an early prototype with 18650 cells, a lot of off-the-shelf stuff. 3D printed bits, antenna deployment. This is getting closer to an actual physical prototype. This was our first original physical prototype that we built, the 1U HeartStar. Here it is in its deployed configuration. Here are some of the boards. The actual boards when they arrive from China. All these things have minimum order quantities, of course, and we're all doing it out of pocket. So the only thing we did do were the actual outer boards. The inner boards themselves are proto board. Because if you've got to order 10 boards, you don't want to order 50 boards for each part of the sat. So here's a dry run of the early assembly. And if this video will work, the very first deployment test, done to NASA standards on the kitchen table, of course. Blue tack's not a structural element, but for the most part it did validate a lot of the design decisions, and it was pretty fun. Bing! So yeah, I was excited, and we've gone through probably every single portion of it's gone through another 20 or 50 iterations in the time since. We're getting close to sort of what we'd consider flight-ready hardware. A lot of it is just sort of raising the funds for launch at this point, and waiting until the stuff is complete. So thanks a bunch. Hopefully we'll see you all in orbit. And let us know if you've got any ideas for interesting payloads for linear electromagnetic accelerators. So, yeah.
Very good to hear that. So one question maybe?
Go for it.
Yeah, so your second CubeSat is actually a linear accelerator you're using.
Yeah, yeah.
You
So
said that the size matters. So,
it does.
But they're very small. So what sort of delta V can you get with?
So we're aiming to accelerate something that's about 1 centimeter by 2 centimeters as a payload, which can at most contain tiny, tiny little sensors and a single chip radio frequency transmitter and just enough battery life to get it through the atmosphere. Something like that, we're hoping to push about 60 meters a second of delta V into, just to get it to skim the atmosphere.
Okay.
Yeah.
Okay. So it's a test.
Yeah, it's a test. And I mean, maybe some that would go through the ionosphere or up to other different levels. So, yeah.
Excellent.
Awesome. Thank you.
Okay. Thank you.